So if you're an optics engineer, you probably would have something like this. This is a photodiode, and this is an amplifier. So in order to use a photodiode, you need to amplify its signal and figure out how much photocurrent the diode makes. So we'll talk about photodiodes, but basically it generates a current depending on how much light falls on it. So it converts photons into electrons and gives a current. And then you need to amplify those because it usually is a pretty small signal. So we have an input here to our amplifier, and we can hook that up to our photodiode, and we can set the range, and it says 30 microamps, so about 30 microamps, 33 microamps. So if I cover up the photodiode, it goes down, and if I uncover the photodiode, light hits it and it goes up. And if I shine a bright light on it, I'm going to get a flashlight here. I'm going to shine a very bright light on it. It saturates, so we're going to have to change the range. And I went the wrong way. There we go. So we're measuring 6 milliamps. So we went from 300 microamps to 11 milliamps. So that's a pretty wide range, and that's why it says large dynamic range amplifier. So this one goes from 100 milliamps full scale to 2 nanoamps. So pretty fancy box, pretty expensive box. I think these are $1,000, I don't know, something like that. Even the photodiode is probably a couple $100. So things in optics land are very, very expensive. And the amplifier also has an output, so you can send that off to a DVM and record these voltages. These currents get converted into a voltage. You can read that with a voltmeter and automate this thing. This is just the amplifier portion of it. So what I'm really interested in is a poor man's version of this. So what can we do to measure light? I'm kind of interested in infrared light. We can't see infrared light, but we know it's there and we'd like to measure it sometime. So what things have infrared light? Well, remote controls use infrared light. Fiber optics use infrared light. Different wavelengths, but it's light that we can't see. So we're going to try to find an inexpensive photodiode and an inexpensive amplifier and build something that's somewhat useful. All right, so this is an old remote control that I have. I was about to throw it away and I thought, no, maybe I can measure it, do some things with it. So it has infrared light, and if I can show that, if I hold down a button and put it next to the photodiode, you can see that we went from 28 microamps up to 90 microamps. So this is outputting light. It's just outputting light at a frequency that I can't see, but the photodiode can see. There's another way that we can see things that we can't see. Optics engineers have a problem with using high-powered lasers that they can't see. They're very, very dangerous. So you wear eye protection, and every once in a while you want to know if the beam is actually on or not. And you don't want to put your hand in the beam and hurt yourself, or you don't want to blind yourself. So you can get these things, which are called, I'm going to focus here. They're called an infrared sensor, but they're just a little piece of plastic. They're just a little card about the size of a business card. And they have a material embedded in this, laminated inside this card. And this material is very, very interesting. If you shine infrared light on it, it glows visibly. And so that's an unusual transition from wavelength to wavelength. I won't get into that, but it does do that. So let me turn off the room lights because it's kind of dark. And I'm going to take my remote control and I'm going to turn it on. And I think you can see that. Whereas if I don't have, if I don't have this card, just drop it on the ground, just have a piece of white paper, you can't see anything. But that card, let me pick it up. That card has this magic goo, and if you shine light on it, it lights up. And in fact, you can see that's actually 2 LEDs inside of this remote control. So they didn't have enough power for 1 LED, they had to have 2 LEDs. And so that's one way to see infrared light. So is there another way to see infrared light? And that's what this video is all about. So I showed a very expensive photodiode and a very large photodiode also. Its active area, its sensitive area is 1 square centimeter. It's a very large piece of silicon to build that diode, and so it's quite expensive. You can get less expensive photodiodes, and here's some that I've collected over the years. If you have an Arduino kit, you might have seen one of these. Let's see here, is this thing going to be in focus? It's hard to see these things. Let me change lenses. Let me go to a macro lens and make this a lot easier. All right, so this is a photoresistor. So as you shine light on it, it changes resistance. So that's not what we're going to use. But that's one way of detecting light that's very inexpensive. There are small photodiodes. Here's one. This one is probably a few millimeters, maybe 10 millimeters active area. It's pretty large. It's like an ATO5 can. But there are smaller ones. Let's see. Here's a smaller one. This is like a TO92 can. It has a little lens on the front, so it's able to focus light. They have 2 legs, they're just diodes. So that's kind of a fun one. There are phototransistors that have the photodiode and a transistor built into the same package. So here's a phototransistor, and you can tell it's a phototransistor because it's got 3 legs on the back. There are photodiodes that look like LEDs, but they're not. Sometimes you see a black LED and you go, well, that can't work. It's just a piece of black plastic, but they're actually an infrared photodiode. I don't think I have any of those in my box here, but here's another type of photodiode. Piece of silicon on a little flat package. That's kind of cool. That's about maybe 300 mil spacing on that. Then there are odd photodiodes that are in a package that look like an IC. So sometimes they're photodiodes mounted this way, but sometimes they have more circuitry. So they might have a photodiode and an amplifier. Or I believe this chip here is a photodiode hooked up to a pulse generator. And so the brighter the light, the faster the pulses. Actually, a lot like the human eye. That's the way our retinas work. So what I'm going to be using, I can dig way down deep in here. These are some photodiodes that were in a product that I built a long time ago, or I didn't actually build it. I kind of worked on it a little bit. Friends of mine designed and built it. But this is a little photodiode in a kind of a short TO92 can, kind of a cute little part. And so that's the one I've decided to use, just because I've got a bunch of them and I think they're quite good quality. So let's take a look at the data sheet for a part like that. Probably want to go back to the other lens. Yeah, let me change back to the other lens. All right, so this is a Siemens part, partially in Deutsch, partially in English. Says it's especially suitable for applications from 350 nanometers to 1100 nanometers. That's a very typical range for silicon photodiodes. They don't work at all wavelengths, but they work in this particular range. So same for CCDs, same for cameras and stuff. It's very difficult to have a silicon-based photoreceptor that goes past 1100 nanometers. So it can't see fiber optics, which is maybe up around 1.2, 1.6 microns. So 1600 nanometers. This one has very low dark current and very low reverse current. It says it's good for exposure meters, automatic timers, and things like that. So what's interesting to take a look at is the sensitivity. You can see that it's sensitive between 400 and 1100 nanometers, but not equally. So it kind of peaks around 800 nanometers, and it's only 20% as good at 400 and only 10% at 1100. So the amount of light that it collects is nonlinear. It's much more sensitive at 800. So need to be aware of that. The other graph that's of interest is this one. And this is a graph of light brightness and photocurrent. And so this line here is the photocurrent. So as the light increases, the photocurrent goes up. Nice straight line. This is a log-log plot, but it's a nice straight line. So it's very, very linear. Photodiodes are very, very linear. This is in units of lux. So if you're in the lighting industry, it's the amount of light that it falls on this piece of paper. So the amount of lux on this piece of paper. So if I had to guess, well, I could get out a meter. We can actually measure the lux here, but it's probably somewhere around 100 to 300 lux, something like that. Operating rooms is actually standard. So in an operating room, we have to have very, very bright lights. And there's actually a standard for how many lux of light that you have to have. So this goes between 10 lux and 1,000 lux, a couple thousand lux. The sun outdoors is about 100,000 lux. Very, very bright. So the photodiode works nice and here, linear. If people say, well, I'm going to use the voltage change of the diode, not the current change of the photodiode. That's this graph here. You read this scale. So actually, the voltage doesn't change very much with brightness, but current does. So it's much better to run photodiodes in this current mode. So let's see what kind of circuit that we need in order to measure current. So we're going to have a photodiode. I'll use the a couple arrows going in. It tells you have a photodiode. And we're going to have a current that comes out. And we need to measure that current. So there's a clever circuit that we're going to use. We're going to use an op amp. And we're going to take this cathode and we're going to wire it up to the negative input. And we're going to take this anode and we're going to wire it to the positive. And you're going to say, well, that's not going to do any good. Op amps always try to make these two inputs exactly the same. So we're going to have some voltage here at the minus and some voltage here at the plus, and they're going to be exactly the same, which means we're going to have 0 volts across the diode, so that's not going to work. Well, in fact, it works just fine, and that's because the photodiode is not outputting voltage, it's outputting a current. So this is called a zero bias circuit. We're not going to put any voltage at all across the diode, but the diode's going to generate a current. So how do we get this thing to measure current? Well, it's going to generate a current in this direction. We're going to put this at ground. It's going to generate a current in this direction. So in order to get this thing balanced, we're going to put a resistor at the top, and we're going to put some voltage at the top, and that will cause a current to flow in this direction. So the op amp sees 0 volts here, it's going to put 0 volts here, so we're going to have 0 here, we're going to have 0 here, and then we're going to have plus V across this resistor. So if the photodiode is generating 1 microamp, then we need to have 1 microamp flowing in this resistor to cancel everything out. All right? So if we have a megohm, we'll need to have 1 volt. So 1 volt across the megohm is 1 microamp, and then everything will balance. So 1 megohm give us a volt. Well, if we take the output of the op amp and we tie it here, then this voltage is going to come from the op amp. So the op amp will see this, it'll see this current, and it'll say, I need to make a current in this direction so that this ends up being 0, and it'll do that by outputting 1 volt. So this circuit will give us 1 volt per microamp. So that's the sensitivity of the circuit, 1 volt per microamp. So if we see 10 volts on the output, we know we've got 10 microamps. If we see 5 volts in the output, we know we have 5 microamps. So that's the way the circuit's going to work. So this is going to be our circuit. And let me draw the exact circuit that we're going to have. So normally you put the feedback resistor on the top like this. We're going to have 220K. We're going to have our little photodiode. And we're going to take the output of this, and that's it. That's all you need. So that's the basics of the circuit. There's a couple tricks to the circuit that you might need to know. One is this thing does like to oscillate at very high frequencies. So in order to stop that from happening, a small capacitor is generally placed here, say 10 picofarads, and that will keep this thing from oscillating at a megahertz or something like that. It could start to oscillate. So generally a little capacitor is put there. So what I thought would be fun is as we shine light on the photodiode, this voltage on the output is going to go up. And if that voltage goes up, then we could put a LED on the output. So if you shine light here, the LED lights. If there's no light here, there's no light here. If there's light here, there's light here. And just in general practice, I put a 220 ohms, and figuring that would work just fine. So this is the circuit that we're going to build, and I'm not going to show the build, and because I've already done it. And here it is. So let me change lenses again, but this is the circuit down here. The rest of the board is just nothing. It's a little prototype area here that I just kind of used. So let me zoom in on that. Okay, here's the circuit. Here's our photodiode down here at the bottom, and here's our op amp, and here's our feedback resistor, our 220 ohm feedback resistor. We have a blue LED right here, and we have our 220 ohm resistor right here, and that's it. we can put 9 volts on this thing and it should run. So let's do that. Turn the power supply on and we'll find some 9 volts. I think this is 9 volts over here. Make sure I get it on the right way. That's ground. And this is plus. And make sure we're in focus here. So I'm going to bring my remote control and I'm going to shine light on the device, and you can see when I push the button, the blue light is receiving. So it's kind of like this is the receiver that I've just built. In fact, it could be used as the receiver. So as I move this away, I'm going to back this off, and you can see the LED gets dimmer and dimmer and dimmer until it finally can't see it any longer. So the brightness of the LED is the intensity of the light. And then it's flashing because this is flashing. If I just have a flashlight that doesn't have any modulation, see, oh, this is not working good. It's not really adjusted for dim light. The problem is if you have visible light, then it's hard to see the part. What I need is a wall between the two. There we go. So if I shine light on this side, you can see the blue light. The blue light is lighting up, and as I get brighter and brighter, the LED gets brighter and brighter. So now we have something that converts infrared light into visible light, and we can use this up to 1100 nanometers. And we can also look at the output on the oscilloscope, and we can see what type of data is coming out of the remote control, so that might be fun. All right, looking at the output of the op amp, and I'm going to put the remote control flashing onto the circuit, and we'll set the triggering here, and we'll set the let me put it into normal trigger mode so it'll capture. So there we go. We're seeing pulses of light coming from the remote control, and we get 1, 2, 3, 4. We get 8. We get 8 pulses, and we can measure the frequency around 38 kilohertz, somewhere around in that region. And if we back up, we see that there's actually a pulse train, and that pulse train is packets of those. So let me zoom in again. Let me zoom in that first pulse. That first pulse is 8 pulses, and then as I move to the next pulse, it's also 8 pulses. So it's always 8 pulses. And then the spaces between these pulses is the encoding. So let me zoom over here to the second. The first one seems to just be, hey, I'm here. The second one seems to change depending on what button you push. So here's 1, 2, 3, 4, 5, 6, 7, 8. So this space here seems to be changing. So anyway, some type of encoding. Probably can make this into 1s and 0s and stuff, but it's a kind of a fun way to look at infrared light.